Okay, well, one thing that we'll notice is that general relativity is actually way beyond the scope of a first year physics course. But we can tell you that basically what special relativity applied is that it allowed Einstein to come up with this field theory. And basically one of the most important things about this is space is four-dimensional. So there's the three standard dimensions that we know about. There's height, width, breadth, but also as a dimension there's time. And that's actually quite important. So he said that basically all of the mathematics involves these four dimensions acting together. And so it's not space-time, it's more space-time. So basically he worked out the mathematics of Newtonian relativity and special relativity and things uses this concept of four-dimensional space-time. He was also working on a couple of other principles, principle of equivalent. Strange as it may seem, there is more than one type of mass. So there's actually a couple of types of mass. There's inertial mass, and this is the classic mass which is used in Newton's formula, force is equal to mass times acceleration. There's also gravitational mass. And this is used in Newton's laws. Force is equal to G M over r squared. But what Einstein was able to do was he basically said that these are the same mass. So the inertial mass and the gravitational mass are the same. So if this is working in a gravity field, it has the same reaction as if it's an inertial mass, if you're using Newton. And this was his classic example. If you're in an elevator and your elevator is accelerating upwards, his argument was, could you tell the difference between these two masses? And basically his conclusion was no. There is no test that you can do which would say whether you're standing in the elevator in a gravitational field or the elevator was accelerating upwards in an empty space. There's no test you can do, and these two are actually the same. And while that seems trivial, I mean, it is actually an important step forward. And so basically what it says, if you're in an accelerating frame or if you're in a gravitational field, the laws of physics work the same for both, and the laws of mechanics work the same for both. But it also meant that it gave us a different way of looking at gravity. So what's gravity? And so gravity, according to Einstein, I doubt that you'll be tested on this, is the curvature of space-time. Space-time. So it's easy enough to space-time. It's easy enough to think of a curve in one dimension. Yay, we curve it a bit. And curve in two dimensions and three dimensions. But when you're starting to talk about curvature in four-dimensional space, that's when people's heads tend to implode or explode, depending what the curvature of the space-time is at that point. So what actually his field theory, because basically his general relativity is like eight field equations, which get pretty ugly for the average person, including me, is that when you have a heavy mass, there's actually a curvature in the four-dimensional space. And the heavier the mass, the stronger the curvature, and the deeper it is. So gravity is basically where you are on that curve on space-time. As the gradient gets steeper, the gravity gets steeper, as it gets higher. As you get further away, it gets less. I mean, the classic way of thinking of this is if you have a big rubber sheet and you drop a marble in here, you get a little curve, a little hole. If you drop a shot put on here, you'll get a big hole. And if you roll the marble past, it'll fall down that hole. Isn't that cool? So, thing is, at the moment, general relativity, special relativity are very good. It's one of the greatest theories of the 20th century. The other great theory of the, or hypothesis theory of the 20th century was quantum mechanics. But at best this is still a partial theory because it still doesn't explain what happens down at the micro level, down at the quantum level. And quantum's a partial level because it doesn't explain, quantum doesn't have gravity in it. Space-time explains gravity by curvature of space-time. Relativity does that, but quantum doesn't have any term in there for gravity whatsoever. So quantum is not a complete theory. General relativity is not a complete theory. So it means at some points general relativity is going to be wrong, quantum's going to be wrong. So, and to quote Dr. House MD, there's no reason why they both can't be wrong. But the reason why we use them is because they work 99.9% of the time. I mean, there's a famous quote, which I'll put up in the lab, all models are wrong. Some are useful. And in this case, general relativity is an incredibly useful model for describing reality. And we are aware of its limitations, but generally this works well enough to make sure our GPS satellites work and to make sure we can predict orbits, and allows us to interface between various things, so, and to explain the expansion of the universe and most things like that. So this at the moment is the best we've got. If you can ever figure out how to join quantum theory and general relativity and relativity together, I promise you this, there is a Nobel Prize in it for you. So good luck.